Chapter 2, Section 2, Day 2, repeating zeros. So this is the same definition I gave you at the end of the last notes. Multiplicity is the number of times a value is listed as a zero or solution. Also, the sum of the multiplicities equals the degree of the polynomial function. And with that information, if you were given a graph like this, and we don't know what these number values A, B, and C are, we're just going to use A, B, and C. We can write the polynomial function by taking the zero, or the solution, turning it into a factor, right? Because you would take the factor, set it equal to 0, and solve, and it would give you the solution, or the 0. So you do that backwards, and it gives you the factors. But then based on the multiplicities, we can get more information than just where the zeros are. So if we look at the first 0, it passes through at A. Since it passes through and nothing really happens, it just in a straight line, that's going to be a multiplicity 1, or an M1, which tells me there's only one solution there. There's only one 0 at A. Now I don't need to write my exponent of 1, but just for this notes example, I'm going to put it in as a 1. So there's 1 0 at A. And then we follow along the graph, and then as it comes down towards the x-axis, it touches B and then goes back the way it came. So it hits the x-axis and bounces off. That tells me I have an M2. So our x minus b factor is going to be a degree 2. And then we follow along our graph, and we have our concavity, we have concave down, and then at C, it changes to being concave up. So that's a point of inflection because the concavity of the graph is changing right there. So that one is an M3, so it tells me I have 3 zeros at C. All right, so M1 is when the graph crosses at the x-axis. Graph crosses x-axis. And M2 is the graph bounces. That's my word. Use that word or not. Any word that makes you think of it touches the x-axis and goes back the way it came from. The off x-axis. And then M3 is the graph has an inflection point. At that 0. All right, so I'm going to add a little note, a little summary type bullet point version note. That odd multiplicities odd multiplicity crosses the x-axis. So even when it's an inflection point at a 3, it's odd, it's still crossing over the x-axis. So any odd multiplicity is going to cross the x-axis. We're not going to deal with multiplicities more than 3, so I'm only going to talk about evens being a 2. But just to a general statement, an even multiplicity will bounce off the x-axis. So if you wanted to see what would happen at different multiplicities, you could use Desmos to type it in to see the graph of different multiplicities, if that's something you're interested in. All right, so an example Today's homework assignment has 3 different sections. Number groups. The first number group is going to have problems like this one, where you're told to find a polynomial function of degree n with only the given real zeros. All right, so for the first one, example A, if you're given 2, 1, and 4, and you're told that n equals 5. So I have a 0 at 2, a 0 at 1, and a 0 at 4, but I have a degree 5. I know I need to use those 3. So f of x equals, I take my 0 at 2, x equals 2, make that the factor x minus 2. And then when the 0 or the solution is 1, that tells me the factor is x minus 1. And 4, the factor would be x minus 4. So I know I have those 3 zeros, but I need a degree 5. This is only degree 3 the way I have it written. So there's a lot of different correct answers. It just depends on which ones you want to repeat. I could say I'm going to use x minus 2 again, and then maybe I want to use x minus 1 again. Or maybe I wanted to use x minus 2 2 times, or maybe I wanted to use x minus 4. Like, there's a lot of different ways you could do this. So then I wrote them all out, but I want to simplify it one time. I have x minus 2, x minus 2, so that means I have x minus 2 is squared. I have x minus 1 and x minus 1, so that means x minus 1 is squared. And then I have x minus 4. I'm not requiring you to multiply these out to standard form. The book solutions are given to you in standard form where they multiplied all this out. I'm fine with it in factored form. If you want to multiply it out, you can. And then the next example is, what if there are no real zeros? So if you have no real zeros, but it's an n equals 4, you have a degree 4 with no real zeros. So if they're not real zeros, then they're imaginary zeros, right? So I could start by writing f of x equals, and there's so many combinations you could go with. I'm just going to go with I. So let's say x minus I, x plus I. That's only 2. So then I'll do it again. X minus I, x plus I. All right, but then I need to simplify it a little bit. So if I just look at a pair of these, this is like the result of doing difference of squares, right? Like whenever you do difference of squares, you have a perfect square and subtraction, and you do square root of the first term, it gives you the first term of each. Square root of the second term, it gives you the second term of each. So, and you get a positive and a negative. So if I were to undo the difference of squares, because I'm trying to go the other direction with it, then this would give me an x squared minus an I squared. Or basically you multiply it out. You could FOIL it. That's the same thing. FOIL it. Multiply it out, the middle terms cancel because one's positive and one's negative. And obviously if I do this pair, it's going to give me the same thing. So x squared minus I squared. But then remember the big rule of dealing with I, that I squared is equal to -1. That's the thing you always have to remember when you're dealing with i's, is that I squared is just -1. But that's what I have right here, is I squared. So that means I could turn this into x squared minus -1. Well, minus -1 gives me +1. Right? And so that means this one would do the same thing. So this also would be x squared plus 1. And if I have two of them and they're exactly the same, that means I have x squared plus 1 squared. So simplifying with I is a little weird, a little different, unfamiliar, probably. That's probably the best word for it, unfamiliar. Okay. But this lesson isn't really so much focused on the I's as it is the rest of it, of the concept. Okay, so then the next one, example 2. All right, this has, in these homework problems, you will have a graph that's printed. So we're just going to recreate one of the book problems, graphs. I'll do it here. And the book counts by 2, so I'm going to make that -2. So this one's -4. So then -6. So then 2 and 4 and 2 and 4. All right, so it gives me a 0 here, a 0 here, and a 0 here. And it doesn't really affect the answer, but the book does show me that I have a y-intercept just below 4. And on the left side, it looked like that. And on the right side, it looked like that. And in the middle, did that. And then it came up and did that. Whenever you do these bounces, you try not to make it real pointy. It really should. It should be more curved. Should kind of hit. It's not super important, but just so you know, it's supposed to be more of a curve, not a jagged bounce. Okay, so first, we're going to decide, is this odd or even? This polynomial, is it going to be an odd polynomial or an even polynomial? And you should be able to tell just by looking at the graph, right? Without doing anything with the zeros. Yeah, you said odd. So odd, because the ends are going in opposite directions, right? That's how we knew it was odd. If they were going in the same direction, it would be even. So this is an odd polynomial. And is it positive or is it negative?
Positive.
Positive. Yes, because like the x cubed function, for example, x cubed, it looks like that. If it's positive, the cubic function, parent function, that's what I think of whenever I'm thinking of an odd, and is it positive or negative? Well, positive is down to the left, up to the right, so yes. It is positive. So I know I have an odd positive function. I need to write the end behavior. I'm okay if you use the abbreviated end behavior that I showed you, but I'm going to write it as the limit. As x goes to negative infinity, the left end behavior of the function equals. So as I go to the left, my function is going down towards negative infinity. The y's are going to negative infinity. That's the left side. And so then the right side, the limit as x goes to positive infinity of the function f of x equals. So on the right side, my graph is going up. The y's are going towards positive infinity. Just as I said, I have odd, and so they're going towards opposite infinities. All right, so then the second part, I need to give the zeros. I'm going to list the zeros. So the first one, and it doesn't matter what order you write them in. I normally go smallest to largest. The leftmost zero is at negative 3. So x equals negative 3. Then I have another one at x equals negative 1. And then I have another 0 at x equals 2. All right, so whenever I get my zeros, I'm going to label their multiplicities. The x at negative 3, that is a bounce off. So I know it's even, but again, because I told you we're only going to go up to a M3, I'm going to say that this is an M2, multiplicity 2, because it bounces off here. So that's an M2. And then I look at the next one. It passes straight through the x-axis. So that's an M1. And then I follow along. When I get to my third 0, it bounces off and goes up again. So that's another M2. So then when I want to write my function, 3, f of x equals, I take my zeros and I write them as factors. So x equals negative 3 is the factor x plus 3. And that is an M2, so I know it needs to be squared. And then I have the factor x plus 1. That's an M1, so I don't need to write an exponent. And then my third factor is at x minus 2. And that is an M2, so it also needs to be squared. And it doesn't matter what order you write the factors in. We'll just leave it there. And really this works as a good set of steps whenever you're given a function, is determine if it's odd, even, positive, negative, and determine the end behavior. Or I guess I could just say it as determine the end behavior, list the zeros with their multiplicities, and then you can write the function. So 3 steps. And then example 3, this one just says find all the zeros. You've been doing this for a very long time, finding the zeros. So if it gives you f of x equals x to the third plus 6x squared minus 4x minus 24, then you're told to find the zeros. Factor and solve should be your automatic go-to for this. I have 4 terms though, so that means I'm going to factor by grouping. Factor by grouping, I group my terms. If your third term is negative, make sure the sign stays with it. So I'm going to group that negative with the 4. And I'm adding these. We're not multiplying, we're adding the groups. And then I look for a greatest common factor from my first group. They both have an x squared, so I can bring out x squared. And then left behind in the parentheses is x plus 6. Then I look at the second group, or I look for a GCF. I know I'm going to want to match x plus 6. So that first term, negative 4x, I want that to be positive, so I'm going to factor out a negative 4. So then I have x plus 6 left behind. My repeating part is a factor, x plus 6. What's left behind is a factor, x squared minus 4. But then, if I am factoring all the way, now these instructions do not say factor and solve, they just say find the zeros. But I want to go ahead and factor it all the way down. And I have x squared minus 4, that's difference of squares. So I have a perfect square minus a perfect square. So I split that up into two sets of parentheses. I make one set positive and the other set negative. Square root of x squared is x, so the first term of each is x. Square root of 4 is 2, so the second term of each is 2. And then bring down my x plus 6. So now I have my polynomial factored all the way. And from there I can easily see the zeros. So x equals negative 6, negative 2, and positive 2. Now because it didn't say factor and solve, if you didn't factor all the way through the difference of squares, you could stop and then solve x squared minus 4 equal to 0. You just make sure you remember to do the positive and negative version of the square root. Okay? So I have 3 solutions of a degree 3. All right, so your assignment is on page 105, and I want you to do numbers 61 through 71 odd, 81 through 87 odd, and 97 through 99. And tomorrow you'll have a homework quiz, and this one is included in your homework quiz. It's 2-1 and 2-2, both parts.